Welcome to the third Manhattan tutorial, which focuses on how to address musical data in other cells around the pattern. The previous tutorial introduced basic code expressions, or formulas, that allow you to programmatically and dynamically set and change values in the music. Formulas can also access data held in other cells in the pattern. To address other cells, a simple XY coordinate system is used, specifying the target cell's channel and row inside square brackets. For example, open square brackets 1, 0, close square brackets represents the first cell in the pattern, channel 1, row 0, whereas 2, 16 represents the cell in channel 2, row 16. There are also many shorthand forms for common scenarios to make things like relative addresses easier. For example, when we don't specify a channel, it defaults to the current channel. Square brackets 32, close square brackets, will address row 32 in the current channel. If we include a plus or minus before our numbers, it represents a relative address. For example, -4 in square brackets represents the cell 4 rows back in the current channel, whereas +1, +1 is the next channel over and the next cell in the future. We can also mix relative and absolute addresses. For example, -1, 8 refers to the cell in row 8 of the previous channel. If we just want to refer to the current row in another channel, we can leave the row blank as well, but we have to include the colon so that the computer knows that we're referencing a channel. For example, 3 on its own references the cell in channel 3 at the current row. We will explore addressing other cells in the pattern through a recreation of Pachelbel's famous canon in D. A canon is a musical form based on repetition, where one part echoes the music previously played by another. In Pachelbel's canon, the first violin plays a melodic part that is later picked up by the second and third, such that the music is played overlapping itself. We will start with a simple example replicating the 8 repeated notes in the bass string part. The 8 notes of the ground bass are provided in the first 32 rows of channel 1, coloured in dark green. These notes repeat throughout the piece unchanged. Rather than using copy and paste, we'll use formulas to copy the rows on the fly. I move to the point in the pattern where I want these notes to start repeating, which is after the first 8 notes play for the first time, row 32. To repeat them, I'll open the formula editor with equals, move up to the expression for the whole cell itself rather than one of its properties, and simply enter an expression that says that this cell is the same as the one 32 rows back, and press enter. Manhattan will highlight how formulas depend on data in other parts of the pattern, using dependency arcs such as the one drawn from row 32 to row 0 in the bass column. However, we don't want to just repeat this row, so I will go down to the cell we created and use the same formula for the rest of the channel by selecting it, copying it, and then repeatedly pasting it so it fills the rest of the channel. Because this is quite a long channel, I will first paste it into a whole bar, and then I'll copy the bar and repeat that so that it fills up more quickly. Now if I unmute this channel and listen to it, I can hear the famous bass line. You can see that it first refers back to the original notes, and then it copies the copy, such that this ground bass section repeats for the entire piece. The canon itself will be contained in the next 3 channels, where the violins play. If I unmute violin 1, I can listen to the melodic part that will be played by all the violins. But for now, only the first violin is playing the music. We will use a very similar process to get the second and third violins to refer back to what violin 1 is playing, and simply copy the music and play it at a later time. First I'll unmute all the channels, and then I will go down to violin 2 and enter a formula for the cell. Again, this is the top row because we are specifying a formula for the whole cell, not an individual property. In this case, we'll do the same thing as we did before, which is to go back 32 rows. But we will also go left one channel so that the second violin can refer to the first violin. Once again, the dependency arcs show how this formula depends on other parts of the pattern. As before, we'll use the same formula for the rest of the violin 2 part. And because violin 3 steals from violin 2 in the same way, we can use the same formula for the third violin. Now if I play the piece, we should be able to hear all the parts of the music. This notably demonstrates that even when you have a complex piece of music, it can be based on a simple underlying pattern and a simple process. If you want an example of the full piece in a single pattern, have a look under the examples in the Help menu and look for Pachelbel's Canon in D. When ready, move to step 2, where we'll move beyond just copying data to copying and changing it. Individual properties of cells, such as pitch, volume and so on, can be accessed using the dot notation. Referencing a cell and then putting dot pitch refers to the pitch in that cell. So for example, brackets 4, close brackets, dot pitch is the pitch in row 4 of the current channel. Brackets 32:0, close brackets, dot volume is the volume in channel 32, row 0. And as before, we can also use relative references, such as brackets -1, close brackets, dot pitch, to refer to the pitch in the cell above the current one. Such mechanisms can be used to create relationships between notes and musical events, shared or linked attributes, where a change in one affects the other. Music has many such relationships between properties, such as intervals and harmony, rhythms and repeats, themes and variations, which can be exploited in formulas. In this next exercise, we will use the cell pitch data to automatically harmonize the ground bass from Pachelbel's Canon. We'll start by muting the original Canon in the first 4 channels of the pattern, and unmuting the yellow channels, where we will place our harmony. In the first cell of channel 5, we'll enter a formula that grabs the pitch from the bass in channel 1 and transposes it up an octave. I'm only interested in copying the pitch, so I enter this formula for the pitch property. I refer to the first channel by going square brackets 1 before the colon, and we will default to the current row by leaving it blank, just closing the square brackets. I want to refer to the pitch, so I put dot pitch, and what I'm going to do is add 12 semitones so that it's an octave higher. We can see how this has created a D4 based on the original D3. I'm now going to harmonize this note by adding formulas to the neighbouring cells that refer to this note and add a certain number of semitones. I do this first for channel 6, entering a pitch formula for the first cell, which references the 5th channel and its pitch, and adds 4 semitones, or a major third. I repeat this step for channel 6 and 7, but add 7 and 11 semitones, respectively for a perfect 5th and major 7th. The harmony that results from this constitutes a major 7th chord built upon the canon's grounded bass. I'll now select this cluster of formulas and use it for each note in the original sequence by copying and pasting it to fill the rest of these channels. We now have a chord progression based on the original ground bass, but when we addition it, you'll notice it sounds a little less like 1690 and a bit more like 1990. Let's now move to step 3 to complete our 90s remix. The remaining channels contain drum, bass, and flute parts that build on your chord sequence and show how simple formulas can use a simple harmony as the basis of a more complete arrangement. Let's first unmute channel 9 and listen to the beat. This channel is based on a drum loop instrument, LM, which is broken up and recycled using the OXX sample offset effect. Notice in the final column of the channel, you get the O command, which is followed by parameters that specify sample offsets within the loop that can be used to skip around within the sample. The XX offset represents the proportion of the loop to skip to in hexadecimal. 00 is the start, 80 is the middle, 40 is 1/4 through, C0 is 3/4, 20 1/8, 10 1/16. Notice how the use of hex, base 16, makes it easy to work with musical times which are often divisible by 16. Recycled loops are usually supplemented with additional drum programming, as demonstrated in channel 10, which provides a percussion part containing hi-hats. Let's listen to this part on its own. And then together with the beat. And together with our harmony. There are no formulas in these percussion parts, which illustrates how Manhattan maintains a flexible balance between writing music as notes and writing it as code. If we now unmute channel 11, we reveal the bass part. This part uses formulas to reference the root note of our chord progression, but changes the rhythm, so we only reference the notes we want to at times we want to, such as in the first cell, where we reference the first pitch and go down an octave, which is then repeated in row 6, using a little helper function called last dot pitch, which just refers to the last pitch. And then in the next beat, we once again reference our chord sequence. Notice how I have skipped out on the second beat, so I can choose when the bass takes from the chord sequence and when it doesn't. Let's listen to it. Notice that by just taking the pitch, I'm also able to add other decorations and embellishments to the music, such as the pitch slides, which are introduced using the E and F effects. Finally, let's unmute channel 12 and 13 and listen to the flute part. The second channel of the flute part is very simple. It simply refers back to the first flute part, one cell across and one cell up, a bit like an echo effect, but one that creates an interesting melodic counterpoint, as the delay echoes notes between subsequent later notes. The flute notes in channel 12, however, are derived from a chord, but they are distributed in time rather than all played at once. If we look in the first 8 rows of channel 12, the formulas show how the flute simply takes from the current chord. This first one takes the root pitch and raises it an octave. The second one, however, takes the pitch from channel 6, now 1 row back in time. The third takes the pitch from channel 7, now 2 rows back in time. And the fourth takes the pitch from channel 8, now 3 rows back in time. This has the effect of arpeggiating the chord, but we don't have to play them in order. In the second beat, we decide to go backwards through the notes, first from channel 8, then 7, then 6, and then to add a little variety, we refer to our current channel and repeat whatever pitch was 2 rows back in time. These 2 beats are then repeated for the rest of the channel. Let's listen to it again. This concludes the third tutorial, which has not only demonstrated how we can refer to data elsewhere in the pattern, but also how we can draw on it using musical relationships in pitch and time to build up a more complicated piece. Like Pachelbel's Canon, which is based on patterns and repetitions, this second example shows how other genres can also be the product of patterns and processes.